For most of human history, there was no reliable treatment for malaria. The disease killed indiscriminately. It hollowed out armies, it emptied villages, it made vast regions of the tropics effectively uninhabitable for those without inherited resistance. Estimates suggest that malaria has killed more humans than any other single cause in the history of the species, a claim difficult to verify, but consistently repeated by epidemiologists who have studied the disease across centuries. And then, sometime in the early 17th century, Spanish missionaries in the Andes learned of a tree. The indigenous peoples of the high cloud forests had long used its bark to treat shivering and fever. The Spanish brought it back to Europe. Within decades, it was the most sought-after medicine on the continent. It was called Peruvian bark, Jesuits' bark, the fever tree. Today we know it as cinchona. The bark contained a compound, later isolated and named quinine, that killed the malaria parasite in the human bloodstream. For nearly 400 years, this tree and its derivatives remained the only reliable treatment for one of humanity's oldest killers. And here is what makes the story strange. In the mid-20th century, synthetic alternatives were developed. Chloroquine, mefloquine, drugs that could be manufactured in factories, standardized in dosage, distributed at scale. They were cheaper. They were patentable. They did not require the slow cultivation of a tropical tree or the uncertainty of agricultural supply chains. Within a generation, the knowledge of how to grow cinchona at scale had largely vanished from the places that once depended on it. Plantations were abandoned. Expertise was not passed down. The tree became a historical curiosity. And then the parasites adapted. Resistance to chloroquine emerged within decades. Resistance to its successors followed. Today, resistance to artemisinin, the current frontline treatment, is spreading across Southeast Asia and into Africa. Meanwhile, the fever tree, the original, the one that worked for 4 centuries, remains where it has always grown, high in the mountains, largely uncultivated, its medicine still effective against strains that defeat modern synthetics. The question is not whether this tree worked. The historical record is unambiguous. The question is why we stopped growing it, and what it would mean to start again. There is a particular rhythm to the history of medicine that becomes visible only when you look across centuries. A treatment emerges, it works, it spreads, it is refined, standardized, scaled. And then, often, it is replaced by something newer, something faster, something that can be manufactured rather than cultivated, controlled rather than grown. This is the story of progress. And sometimes it is also the story of loss. Malaria is one of the oldest diseases known to humanity. References to its characteristic fevers appear in Chinese medical texts from 2700 BCE. Egyptian mummies show signs of infection. Greek physicians described it. Roman engineers drained marshes to escape it. The name itself comes from the Italian malaria, bad air, reflecting centuries of misunderstanding about how the disease spread. What was never misunderstood was its lethality. Malaria killed infants and emperors. It determined which armies could march and which could not. It shaped where cities were built and where they were abandoned. For most of human history, there was no effective treatment. Fevers came. Some people survived, many did not. And then, in the 17th century, something changed. Spanish colonizers and Jesuit missionaries in the viceroyalty of Peru encountered a tree that grew in the cloud forests of the Andes. The Quechua people of the highlands had long used its bark for various ailments, including fevers. The Spanish, suffering from the same fevers that plagued lowland settlements, began experimenting with the remedy. The results were dramatic. The bark worked. Not sometimes, not partially. It worked consistently, reliably, in ways that no European medicine had ever worked against the shaking chills and burning fevers of malaria. By the 1640s, the bark was being shipped to Europe. By the 1650s, it was in high demand across the continent. It was expensive, so expensive that it was often called the bark of kings. But for those who could afford it, it was the difference between life and death. The tree had no common name in European languages. It was called simply Corteza del Peru, Peruvian bark. Later it was called Jesuits' bark, because the missionaries had been so instrumental in its spread. Later still, the Swedish botanist Carl Linnaeus gave it a Latin name in honor of the Countess of Cinchon, a Spanish noblewoman who allegedly benefited from the treatment, though the details of that story remain disputed. What is not disputed is the effect. For nearly 400 years, this tree and its derivatives remained the primary weapon against malaria. The active compound was isolated in 1820 by French chemists and named quinine. But long before anyone understood the chemistry, the medicine worked. And here is where the story turns strange. In the 20th century, synthetic alternatives were developed. They were cheaper to produce. They could be manufactured in laboratories rather than cultivated on mountainsides. They could be patented. The tree was abandoned. Plantations that had supplied the world were left to grow wild, or were cleared for other crops. The knowledge of cultivation, how to grow the trees, when to harvest the bark, how to process it for maximum potency, was not passed down. And then the synthetics began to fail. Chloroquine resistance appeared within decades of the drug's introduction. Resistance to subsequent drugs followed. Today, the malaria parasite is evolving resistance to artemisinin, the current first-line treatment derived from a different plant entirely. Meanwhile, there is no widespread resistance to the fever tree's bark. The compounds still work. The tree still grows. The knowledge of how to cultivate it at scale has simply been allowed to fade. This is not a film about what should be done. It is a film about what was lost and why. The history of this tree is inseparable from the history of empire. When the bark arrived in Europe in the mid-17th century, it arrived into a world that had no defense against tropical disease. European armies and colonizers had repeatedly attempted to establish permanent presence in malaria-endemic regions, West Africa, South Asia, the Caribbean, and had repeatedly failed. The death rates were catastrophic. The bark changed the equation. By the 18th century, the British East India Company was purchasing vast quantities of Peruvian bark to protect its employees in India. The Spanish and Portuguese used it to maintain their colonial holdings in the Americas. The French used it in their Caribbean plantations. The demand outstripped supply almost immediately. The tree grew only in a narrow band of the Andes, at elevations between 5,000 and 9,000 feet, in conditions that could not be easily replicated elsewhere. Wild harvesting stripped the bark from trees faster than they could regrow. Prices soared. Adulteration became common. Unscrupulous traders mixed inferior barks with genuine cinchona, weakening the medicine and endangering lives. By the early 19th century, the governments of Europe recognized that whoever controlled the supply of this bark controlled access to the tropics. The Dutch, the British, and the French all launched expeditions to obtain seeds and plants. The South American nations where the tree grew naturally, by then independent of Spain, attempted to prevent the export of viable specimens. They understood what was at stake. But the seeds were smuggled out anyway. The British botanist Clements Markham led an expedition in 1860 that successfully obtained seeds and young plants from multiple species. The Dutch mounted similar efforts. By the 1870s, experimental plantations were established in India, Ceylon, and Java. Not all attempts succeeded. The tree was finicky. It required specific conditions, the right elevation, the right rainfall, the right soil acidity. Many plantations failed before they produced a single harvest, but the Dutch succeeded in Java. By the 1890s, Dutch plantations in the highlands of Java were producing more bark than the wild forests of South America. The Dutch controlled global supply. They established a quinine cartel that set prices and regulated exports. They bred new varieties with higher alkaloid content. They refined processing techniques. By the early 20th century, Java supplied over 90% of the world's quinine. This concentration of supply would prove significant. When Japan invaded and occupied Java in 1942, the Allied powers lost access to their primary source of antimalarial medicine. American and British troops in the Pacific and Southeast Asia suffered malaria rates that sometimes exceeded combat casualties. The shortage was so acute that it became a strategic crisis. This crisis accelerated the development of synthetic alternatives. Chloroquine, first synthesized in Germany in 1934 but initially overlooked, was rediscovered and put into mass production. By the end of the war, the Allies had a synthetic antimalarial that did not require tropical agriculture, did not depend on a single island in the Dutch East Indies, and could be manufactured at industrial scale. The bark that had shaped 4 centuries of history was no longer essential. The transition was rapid. After World War II, synthetic antimalarials became the global standard. Chloroquine was cheap, effective, and easy to distribute. International health campaigns deployed it across Africa, Asia, and Latin America. The World Health Organization launched its Global Malaria Eradication Program in 1955, built largely around the widespread distribution of synthetic drugs and the insecticide DDT. The tree became obsolete. Plantations in Indonesia, India, and Africa were abandoned or converted to other crops. The expertise required to cultivate, harvest, and process the bark was no longer economically valuable. The generation of farmers and agricultural scientists who understood the tree aged and retired without training successors. By the 1970s, commercial cultivation had declined dramatically. The bark was still available. Wild harvesting continued in South America, and some plantations persisted, but it was a marginal product, used primarily for the bitter flavoring in tonic water rather than as a frontline medicine. This might have been the end of the story. A successful handover from plant to laboratory, a rational modernization. Except the parasites did not cooperate. The first reports of chloroquine resistance appeared in the late 1950s along the Thailand-Cambodia border. By the 1960s, resistance had spread to South America. By the 1970s, it was appearing in Africa. The response was to develop new synthetics: mefloquine, sulfadoxine pyrimethamine. Each worked for a time. Each eventually faced resistance. The pattern was consistent. A new drug was introduced. The parasite evolved. The drug became less effective. A newer drug was needed. This is the fundamental challenge of single-compound pharmacology. A synthetic drug typically works through a single mechanism, a specific molecular target that disrupts the parasite's life cycle. The parasite, under selective pressure, eventually evolves mutations that circumvent that mechanism. The more widely the drug is used, the faster resistance develops. The fever tree works differently. The bark contains not one alkaloid, but several. Quinine is the most abundant, but quinidine, cinchonine, and cinchonidine are also present in significant quantities. Each compound acts through slightly different pathways. Each contributes to the antimalarial effect. This multi-compound profile makes resistance far harder to evolve. The parasite would need to develop simultaneous mutations against multiple targets, a far less likely event than developing resistance to a single compound. This was understood, at least partially, even before the chemistry was fully characterized. Early 20th century researchers noted that crude bark extracts sometimes outperformed purified quinine against resistant infections. The whole was more effective than the sum of its parts, but crude extracts were difficult to standardize. They varied in potency from batch to batch, tree to tree, harvest to harvest. They did not fit the pharmaceutical model of precise dosing and reproducible formulations. And they could not be patented. A purified compound, a synthetic molecule, a novel chemical entity, these could be protected by intellectual property. They could generate returns on research investment. They could be manufactured at scale with consistent margins. A tree that grew in the mountains, whose bark contained a variable mixture of alkaloids, whose cultivation required years rather than weeks, this was economically inconvenient. The system did not suppress the tree. It simply found the tree unnecessary. The economics pointed elsewhere, and the knowledge followed the economics. The current frontline treatment for malaria is artemisinin, derived from a Chinese herb called sweet wormwood. Artemisinin is fast-acting and highly effective. In combination with other drugs, a strategy called artemisinin combination therapy, or ACT, it has saved millions of lives since its widespread adoption in the early 2000s. But artemisinin resistance is spreading. First detected along the Thailand-Cambodia border in the late 2000s, the same region where chloroquine resistance first emerged decades earlier, resistance to artemisinin has now been confirmed in multiple countries in Southeast Asia. Cases have been reported in Africa. The pattern is familiar. The cycle is repeating. This has prompted renewed interest in alternatives. Researchers are investigating new synthetic compounds, new drug combinations, new approaches to vector control. Some are looking backward as well as forward. The fever tree has not been forgotten by scientists. It remains a reference point in antimalarial research, a benchmark against which new treatments are measured. The alkaloids it contains are still used. Quinine is administered for severe malaria cases, particularly when other drugs have failed. Quinidine, a closely related compound, is used in cardiac medicine. But large-scale cultivation has not resumed. The expertise that once existed in Java, in India, in British colonial agricultural services has largely dissipated. The land that once supported plantations has been converted to other uses. The global supply chain for bark-derived quinine is thin, fragmented, dependent on wild harvesting and small-scale cultivation in regions with little infrastructure. If artemisinin combination therapies fail, if resistance spreads faster than new synthetics can be developed, the capacity to scale up bark production quickly does not exist. This is not a hypothetical concern. Epidemiologists and public health officials have been writing about it for years. The vulnerability is documented. The gap is known. What is less known is what it would take to rebuild. The tree is not difficult to grow, given the right conditions. It requires elevation, the highlands of tropical regions, between 5,000 and 9,000 feet. It requires significant rainfall, 60 to 80 inches per year in most cultivated varieties. It requires years of patience. A tree planted today would not yield harvestable bark for 6 to 10 years. But the tree is not fragile. It is not temperamental. It grows in poor soils. It tolerates the conditions of cloud forests and mountain slopes. It is, in agricultural terms, a survivor. The knowledge required to cultivate it still exists, scattered in agricultural archives, old colonial records, the memories of aging foresters in South American highlands. It has not been destroyed. It has simply been neglected. The tree is called cinchona. The name refers not to a single species, but to a genus, a group of related trees and shrubs native to the Andean cloud forests of South America. The species that have been most extensively cultivated and studied include varieties from Peru, Ecuador, Bolivia, and Colombia. The common name, fever tree, reflects the use that made it famous. But the tree itself is unremarkable in appearance. It grows to modest heights, with broad leaves and small clusters of flowers. There is nothing in its form that suggests its importance. It still grows wild in the Andes, in the same cloud forests where it was first discovered by European colonizers 4 centuries ago. The Quechua people who first used its bark still live in those highlands. It still grows in the scattered remains of colonial plantations in Indonesia, in India, in parts of East Africa, where abandoned trees have persisted, sometimes for generations, without cultivation or care. It can still be grown. The conditions are specific but not rare. Tropical highlands exist across the globe. The seeds, while not common, are available. The cultivation techniques, while not widely taught, are documented. For those who wish to understand the tree rather than simply read about it, the path is straightforward. The bark can still be purchased, powdered in chunks as tinctures from herbalists and specialty suppliers. Tonic water, though it now contains far less quinine than it once did, still carries a trace of the original bitter flavor. The taste is distinctive, intensely bitter, almost medicinal, This is the flavor that British colonial officers masked with gin. This is the flavor that signaled to generations of malaria sufferers that the medicine was real. The tree does not advertise itself. It does not need to. It has outlasted the empires that fought over it. It has outlasted the synthetic drugs that replaced it. It continues to grow in the same mountains where it has grown for millennia, producing the same alkaloids, offering the same protection. What was lost was not the tree. What was lost was the system that knew how to use it. The plantations, the expertise, the supply chains, the agricultural knowledge passed from one generation to the next. That knowledge can be rebuilt. Whether it will be rebuilt is a different question. But the tree remains. It simply waits.